Hello, today we will be discussing about fuel cells. Fuel cells are those devices which generate electricity from a electrochemical reaction. And in this electrochemical reaction, oxygen from air and hydrogen, they combine to form water. So this is the basic reaction of a fuel cell: oxygen and hydrogen combining water, and the electricity produced or the electrons produced, they contribute to the electricity occurring in fuel cells. The, all there are different types of fuel cells, but the basic reaction remains the same. There are different types of fuel cells. I can have an alkaline fuel cell, direct methanol fuel cell, molten carbonate fuel cell, phosphoric acid fuel cell, proton exchange membrane fuel cell, solid oxide fuel cells, regenerative fuel cell, and metal air fuel cell. So although these are the different types, but the basic reaction of hydrogen and oxygen coming together to form H2O, this basic reaction remains the same in all these types. Now coming to the construction of a fuel cell, as every battery or every cell, it consists of two electrodes. One is positive, another one is negative. It consists of an electrolyte which can be either in the solid state or in the liquid state. We can have so like in any battery, the the charge particles are created inside the cell, and this production of these charge particles or can be accelerated by using a catalyst which can be platinum, for example platinum, which can speed up the electrochemical reactions forming water, H2O. Now coming to the construction, if this is your fuel cell, these are the two electrodes, and here we allow the oxygen gas to pass in, go inside. Here is where there is a barrier between the two electrodes, uh, and here is where the hydrogen gas comes out, and whatever reactions takes place, the electron flow takes place between the two electrodes. So this happens to be the cathode, which collects the electrons, and this happens to be the anode, which accepts the electron, where oxidation takes place. So this is the basic construction. Coming to a more detailed view, the hydrogen, it gets oxidized to H plus, which is also called proton, and it occurs at the anode. Now these protons, these protons H plus, they will move inside the fuel cell through the electrolyte. And it will try to reach the cathode, where the oxygen is in the reduced state. That means is in a higher negative state. So this excess negative state of the electron is neutralized by the protons coming from the anode, which results in the production of water as hydrogen and oxygen meet, and this production of electron causes an external electricity flowing outside the fuel cell. So let's talk about the chemical reaction that takes place. So at the anode, we have H2, which is in the gaseous state. This is the fuel. This converts into 4H plus. You write 2H2 here, and this is in the aqueous state through the electrolyte, and there is production of electrons. These are the electrons responsible for the electricity generation. And at the cathode, oxygen, which is also in the gaseous state, it accepts the electrons, it accepts the protons coming from the anode as well as the 4 electrons, and it leads to production of 2H2O. So the overall reaction, if we add up these two reactions, this is 2H2G plus O2 in the gaseous state, giving rise to water. Okay, so you can see that there are no electrons produced here. So it means that whatever electron is produced at the anode is passed on. So if this is the electrons produced, these electrons don't pass through the electrolyte. They pass on through an external circuit. Again, and this is the reaction that is taking place inside the cell, where the flow of electron taking place outside the cell. Right. So this is how the fuel cell works. Now coming to a little more details of the other parameters involved. If you talk about the efficiency of a fuel cell, it is basically the thermal efficiency, which can define as the percentage of useful electrical energy produced. It's the percentage of useful electrical energy. produced relative to the heat. It's relative to the heat that would have been obtained through the combustion had the fuel been subject to any combustion. So it's the useful electrical energy with respect to the relative amount of heat, and this efficiency is also called enthalpy of formation. And mathematically it is given as delta G divided by delta H is the efficiency of the fuel cell. Now, the highest possible efficiency that can be obtained in a fuel cell is 83%. Oh, now this 83%, considering this efficiency, there is another way of representing the efficiency in terms of the potential corresponding to the ideal one. So if you would like to find out the efficiency, you can also write it as 0.83 divided by V cell, the potential inside the cell, divided by voltage in the ideal conditions. This is also a definition of efficiency. Now, what is the difference between an ideal and non-ideal condition? Now, in a non-ideal condition, so we'll take it as the ideal. So, in a non-ideal condition, what happens is that the actual operating voltage is less than the ideal voltage. So, V cell, which is the actual operating voltage, is always found to be less than the V ideal. Now, why this thing happens? This happens because of some losses taking place inside the fuel cell. Okay, now going to that. Losses in fuel cell. So basically three types of losses which degrades the performance of a fuel cell. The first one is called activation polarization. The second one is called ohmic polarization. And the third one is called concentration polarization. The interesting thing is that these losses are represented in terms of this thing, polarization. The losses are represented in terms of polarization. What this polarization actually means and how is it so much significant in fuel cell loss? Now, as you might have observed that during a fuel cell, the the whole process of the electrochemical reaction, which is producing electricity, depends upon the joining of or the meeting of the charges. The protons, it meets the already produced negative charge. Okay, now if we somehow would not allow these charges to move, rather if we separate out the charges at two extreme ends, then this will be considered to be an degradation towards the performance. Now, as you know, the separation of charges is termed polarization. So that is how the resistance or the inefficiencies caused has been termed polarization due to separation of charges. So put all these three efficiencies, they actually are doing the same thing. They are not allowing the positive and the negative charge to come together, to come close together. Now, if we try to represent graphically, so if we plot the cell voltage here and the current density here, so write it down here. So this is the current density expressed in milliamp per centimeter square, and this is the cell voltage V cell. So the typical plot of a real cell, it actually looks like this. Okay. Now there are three regions corresponding to the three different losses. So we take the full voltage as 1.0. So this is where the activation polarization takes place. Call it as activation polarization at the higher voltage and lower current densities. So this is 200 to say 600. After activation polarization, next come is your ohmic polarization in this range, and lastly you have concentration polarization. So this actually, the three polarization, they define the shape of the cell volt or shape of the IV curve of a fuel cell. Now let us try to understand what these three polarizations are. We take up the activation polarization first. Activation polarization occurs due to limited reaction rates that are inside the fuel cell. And it is expressed as log of I by I0, where I is the exchange current density in the ideal case, and I is the exchange current density. Alpha is the electron transfer coefficient. This is electron transfer coefficient, and RTIs are the, this is the gas constant, this is temperature, this is number of electron charge density, and this is farad. So due to the limited, if there are some limitations that are present in the electrochemical reaction itself, and this occurs mainly at the surface of the electrodes. So electrode surfaces, if they are not pure or they have got some impurities in it, so the electrochemical reaction rate is slow, and it adds up to the activation polarization taking place. Now similarly, if we talk about ohmic polarization, now from the name itself we can understand that it is related to Ohm's law. V is equal to IR, so we will write ohmic polarization delta H ohm is equal to simply IR. Okay, so it is the as we have resistance towards flow of current through a metal wire. Similar to that, when there is a flow of electron, it causes a resistance, and this R is the total resistance, which includes the ionic and electronic contacts as well. So whenever we have got a contact, say if this is your fuel cell, this is the electrodes and this is the flow of electrons, you can see there are two contacts. taking place. So in these contacts, the resistance is actually more prominent. The ohmic resistance is actually more prominent. And lastly, we have concentration polarization. And this occurs as the reactant is consumed at the electrode. Okay. If the reactant, or the one that is used in the reaction, if it gets consumed at the electrode, it causes loss of potential due to the inability of the surrounding material to maintain the initial concentration. Right, so this is the electrode, and the reaction has taken place, which has caused some degradation or lowering concentration of the fluid surrounding it, and the surrounding materials are not able to maintain the concentration due to the reaction, due to the consumption of the reactant. Then there is a formation of a concentration gradient. Concentration gradient is formed, and this is the basically is called the concentration polarization. It is expressed as call it eta concentration is equal to, similarly, RT by NF log of 1 minus I by IL. Well, IL is called the limiting current. So this is the limiting current.